past week or so, we've introduced a bunch of different concepts that I'm going to try to bring together right now. One was protected control transfer. How do we hand over control to the operating system? The other was how do we represent address spaces and how do we do this partnership between the hardware and software? So we're going to bring all of those together by walking through what happens when the hardware doesn't have the mapping it needs to do a translation. So let us start with protected control transfer. You might remember we introduced this in the concept of a disk drive, and we said that when we get an interrupt, we dispatch through this trap handler table and ultimately end up executing in the operating system. Well, let's look at that in the context of a TLB fault. So our user process is happily running along. It's generating addresses, they're getting translated by the processor, and life is good, and the operating system is kind of out to lunch. But all of a sudden, the user process can generate an address that isn't mapped in the TLB. At which point the MMU or the processor throws up its hands and says, I can't do anything with this. I don't have a mapping for it. No problem. I know what to do when I don't have a mapping. I'm going to generate a trap. The trap is going to turn over control to the operating system. Given the particular trap number, in this case, it's going to be a TLB fault. The operating system will say, oh, I know how to do that. I'm going to go into the right trap handler. Now, there exists some hardware that can handle TLB faults because they actually know how to read page tables, right? They dictate to the operating system how page tables are structured so that the hardware can actually read the page tables. We'll talk about that in lecture when we introduce the x86 specific implementation of virtual memory. But for now, let's assume that we don't have a mapping in the TLB, we just turn over control to the operating system. What is the operating system going to do? Well, it's going to find the page table, and then it's going to look up the entry that the process is trying to access. So one piece of information that the operating system gets is, in fact, the faulting address, right? Here's the virtual address that I couldn't handle in the hardware. And then depending on what the PTE says, we're going to do one of a few different things. So let's look at the different things we might do. If the entry is invalid, we're going to have to kill the process. Maybe the entry's valid, maybe it's even in memory. You have the right permissions, it's just not in the TLB. No problem, we'll load the TLB. The third case is the one we'll spend most of our time on, which is, it's a valid page, but it's not here. Like I have to go find it. So let's walk through these different kind of samples. So this is a picture of main memory on the right. So still a relatively small memory, although a little bit bigger than our 16-bit virtual address space, so we can have multiple processes here. The dark blocks are the blocks that the operating system is actively using. So I, as the operating system, have to manage lots of data. I need space to do that, so those are my blocks. The light gray are blocks that no one's using, so those I'm free to allocate to address spaces. And then I currently have 3 processes running, and each one has some data here. So I'm in my trap handler. First thing I do is I go look at the PTE that corresponds to the faulting address. So one case might be that I look at that PTE and there's some specific value in there that tells me this PTE is invalid. It's not supposed to be part of the address space at all, right? So it doesn't matter whether it's present or not. This bit on the right indicates whether the page is in memory. If the page is invalid, it's certainly not present. And so what I'm going to do, in contrast, we might have information that says it's valid, but let's focus on the first case where it says there's no page here. That's the case where we're going to generate a seg fault and say, no, 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 you don't get to access, and I get to kill the process. All right, so that's kind of the easy case. But now let's imagine that I have a PTE that says, yep, this is part of the address space. I'm going to ask the question, say, well, is the page currently present in memory? So I'm going to do that by looking at the present bit. So there's some bit in the PTE that says, is this page in memory or not? And I'm going to look at that. And if it is, I can say, okay, the page is here. I can check the access permissions and things like that. But if that present bit is 0, then what the information in the PTE is going to tell me is, where do I find the information I need? Like, where is this page? And as we talked about, when we talked about page tables, sometimes you get to like create pages out of thin air, where thin air is zeros and they're 0 filled, or sometimes the page lives on a device. And so that PTE will tell you both what device it lives on and where on that device. So you can think of it as saying it's a specific disk drive and it's a specific block on that disk drive. And that's where I need you to go get the data from. All right, so we check whether it's present. Let us assume that it's not present. What I now need to do is like, okay, I'm gonna have to create this page. So the first thing I do is I look at main memory, and I have to have a data structure to keep track of this main memory. And I say, I need a free page. So this is just a normal dynamic memory management problem. Fortunately, they're all fixed size things, so it's a pretty easy dynamic memory management problem. So I find a page. Say, great, here's your page. Now what I'm gonna do is I'm gonna fill that page with valid data. Either go to disk and read it, or just write zeros in it. So now I put the contents in the page. Now I've got a valid page. It can be part of your address space. So I go and I update the PTE and say, oh, that page you wanted, here's where it lives. So I change that entry from saying it lives on disk somewhere to here is where it lives in main memory, here is its physical page number. And then once I've got that, I just say, okay, go run that instruction again. And I quite literally restart the instruction because that instruction couldn't do anything because it couldn't access the data because it wasn't there. But if I run that instruction again, now the data's there, life should be good. So that's how we handle these faults that the hardware tells us about when it can't do the translation. And so the software's job is really to determine whether it can proceed or not. Should it just kill the process? It has to potentially load the TLB. It might have to go allocate a page. It might have to fill that page. It might have to read something from disk, and it might have to update some page table entries. And it better do those in the right order. And we'll give you some practice checking out that order.